The topic on the floor is kinematics, the motion of points in space, in particular in the plane. And we are going to make a special use of this nifty little idea called intermediate frames, also known as body coordinate systems and so forth. And in particular, last time we introduced these formula for what we're going to do today. I'm going to go over these formula we introduced last time because they're just a little off-putting, I have to say, to most people. And then because of that, I told you last time I was going to show you how to derive them. The derivation is in your book, and I made a judgment call that actually our time would be better spent if we worked through some examples about how to use the formulas, not necessarily where they came from. I recommend you read the book to understand fully where they came from. That'd be chapter 3 in the textbook. But today, I'd really like to focus on essentially how to use the formulas, because that, in my opinion, is where the tough part is. That's where the rubber meets the road. Okay, and with that, oh, wrong button. Here we go. Let's bring these guys down. First off, let's review the bidding. Let me just check my understanding. Is it a fair statement? Anybody come away from last Thursday's lecture a little confused, a little uncertain as to how this all worked? Yeah, okay, fair enough. Good, so I'm not wasting my time here. But my sense of it is that this is a very useful concept that it kind of behooves you to get your mind around. So let's review the circumstances. So here is the situation. This diagram right here illustrates the basic situation. We have a fixed coordinate system or world coordinate system, big O, big X, big Y, might be big Z, with unit vectors, cap I, cap J, cap J and K. And in that coordinate system, moving about, flying about, translating, rotating, and so forth, as we illustrated last time, is a rigid body. The rigid body can be translating, it can be rotating, it can be accelerating, both linearly and rotationally. And here is where the kind of subtlety comes in. We get to choose. We get to say, by choice, I would like to designate a point on the rigid body, call A, where my fixed coordinates, or excuse me, where my body coordinate system is going to originate, and I get to choose little x, little y, and the corresponding unit vectors that go with it. I get to choose these guys. I get to choose not only the point where I want the body coordinate system to emanate from, but I get to choose the little x and little y directions of that fixed coordinate system, or that body coordinate system. All righty? So, now, the whole objective of this exercise is to keep track of something. There's some point we're going to call B, and we're going to call the origin of that fixed coordinate system A. We're going to call the point of interest, shall we say, B. We're going to call it B, and we're going to describe the location of B on the fixed body, or excuse me, on the rotating body, in terms of its location in the body coordinate system. And now here's the kind of tricky part. Can you guys read this in the back? Is that clear? You cannot read that. All right. Very good. This is a perfect opportunity to emphasize the point, no pun intended, point B is not to the rigid body. All right, as we pointed out last time, whereas the body coordinate system is fixed, point A and the body coordinate system is absolutely fixed to the rigid body as it's rotating or wherever it goes. The point we speak of doesn't have to be. The point in question can be moving around with respect to the body coordinate system, which is itself moving through space. Clear enough? Complicated enough? I would assert this is, the reason we spend as much time on it as we do is this is arguably the worst possible case. Everything is moving. So it's not going to get any worse than this. So if you can learn to wrestle this to the ground, you're home free. All right? And again, just to review the equations of last time, notice that the position of point B, where is it? The position of point B, this is key, the position of point B in the world coordinate system, in the fixed coordinate system, is given by this equation. R sub A, which is described in the fixed coordinate system, in the world coordinate system, okay, plus R sub AB, the vector from A to B, which is not, okay? R sub AB is defined with respect to this body coordinate system that's running around in space. So while big I hat, big J hat, big Z hat are fixed in time, are not changing with time, not so the little guys, not so little I hat, little J hat, and so forth. Everybody clear? And in fact, the point I'm going to make here in a moment is this is the point. It is this whole scheme was devised precisely because many times it is more convenient to describe positions and velocities and accelerations in body coordinate systems that move around and than it is to describe them here. And so these are means of essentially mapping that all back home, so to speak. So anyway, this is the position of point B in the world. This is the velocity of point B as seen from the ground. Once again, you can see that it has components. It has this first one, V sub A, which is nothing more than the time derivative of this guy, also described in the fixed coordinate system. Then these two terms, which we described earlier, which contain, excuse me, I forgot to put this guy here. This rigid body is not only rotating, but it not only has angular velocity, but it has, in general, angular acceleration as well. Whereas this is simply the translational velocity of the point you chose, this is the contribution to the velocity, to the linear velocity of point B, seen on the ground, the contribution of that from just the rotation. Does that make sense? Just the rotation. And this, which is the derivative here, is the contribution that comes, okay, from that. Once again, now onward to acceleration. The acceleration, again, of point B in the world coordinate system. It's got this, when you differentiate, it just breeds terms like coat hangers and closets. They just, we now have 5 terms. That's a colloquialism where I come from. There is the first term, A sub A, is simply the second derivative of R sub A. It's simply the linear acceleration of the point A, the origin of the body coordinate system that you chose. This term right here, alpha cross RAB, is simply this, and this is the one they call the Eulerian term. This one the centripetal. And this one, the Coriolis. Okay, and so this is the, I'm skipping ahead, this is the Eulerian, this is the centripetal, and this is the Coriolis. This one is the acceleration. Yeah, what is this? How about the lady in black there? What's your name? Tori. Tori. What's that one? What does that mean? What's the kind of physical significance of it?
For the acceleration.
It's an acceleration for sure. What'd you say?
It's relative to the local for the, yeah.
Precisely. Excellent. Tori, you said. Yeah, Tori, the spot on here says a rel is the acceleration of this guy in the local coordinate system, in the body coordinate system. Everybody with me? All right, so that's a review of the bidding. Any questions before we go further? Because it's going to get deep pretty quickly here. Hearing none? Wonderful. There's at least 2 explanations possible for no questions. I'm going to assume the positive one. Okay. Now here's a question that got relayed to me. And I thought this was worth answering. So it said, is the rigid body rotating about point A? Okay, and the other is point A an instantaneous center of rotation? That's a good one. That's a real good one. Hey, Tori, you're on a roll here. How about tackling this last one? Is point A an instantaneous center of rotation? You got a 50-50 shot. Just
Okay, yes.
say yes, it is. How about the lady right next to you? You're Kate?
I'm Isabella.
Isabella?
Yes.
She says yes. All right, how about the lady right next door?
Just gonna change it up and say no.
Just say no. Perfect. Wonderful. So we got 2 yeses and a no, which is perfect. The correct answer is sometimes it is and sometimes it isn't. All right. So this is the point. I'd like to just stomp this out really quickly here. You guys remember the example of the rolling wheel. Okay, non-slip rolling. This is a stone, caveman's stone wheel, or a Bridgestone tire, or a little frisbee rolling on edge, doesn't matter. Situation is it's a cylinder of radius r, okay, and it has an angular velocity omega, and we're going to presume a fixed coordinate system over here someplace. Don't know exactly where. This. Okay, so let's just talk tires here for a moment. Again, if you're car people, if you're driving down the road at, say, 70 miles, or wait, you guys, let's say 55. Okay, 55 miles an hour. So I got to behave here. How about it? The man in the front row, gray shirt. What is the, oh, never mind, I already wrote it here. What's the linear velocity of the center of the wheel? Let me put it here. I wrote this here. So you have good reason to believe the answer is omega r I hat. Now, question I would ask of you, where did that come from?
So that came from doing omega cross r. Yeah, omega.
Yeah, one of these in here. Yeah. All right, I tell you what I wanted to do here, I wanted to get across the fact that this is the physics. This is the physical thing. All right, this is a wheel. It's rolling down the road with a certain angular velocity. The point at which it contacts the ground is not slipping. So we went through that whole exercise last time that conceptually the entire object is rotating about this point with that angular velocity. And so the linear velocity of any other point you choose is obtained by simply taking omega cross r. Right? Remember that? Okay, so you know that. So you know, so that what that says is if your axle is doing 70 down on 93, the top, a little particle on the top of the tire is doing 140 miles an hour. Interesting idea. And at that very instant, the particle that's at the bottom of the tire is going nowhere. All right, it's just one of those. All right, so here we come, and let's do this. Let's see, Isabella, which one did you choose? Did you say, were you a yes or a no? You were a yes, perfect, okay. So Isabella is going to come along and say, well, here's how I do this. They told me I could choose A, and I could choose little x and little y, all right? So Isabella comes along and says, here's what I'm choosing as point A. So here's r sub A, okay? And again, point B, this is the one we're interested in. This is the point of interest. So Isabella says, here's r sub B, so that makes this r sub AB, correct? Okay, Isabella, do the math for us. I want you to apply this formula. This formula right there. Yeah, talk me through all the pieces. Talk me through the pieces. Talk me about, how about V sub A? V sub A is 0. How come? Pardon?
Point A is not moving.
Point A is not moving. Excellent. V sub A is 0. So that one's gone. How about this VREL, whatever the heck that is? VREL. Ask Tori. Hey, Tori. Isabella wants to know what VREL is, just for a moment. What's VREL? Oh, Isabella, maybe she doesn't need to know. Let's hear it.
Is it 2 omega r? No, it's not.
Yes, yes, no, maybe. All right, the lady next to, I've forgotten. What's your name again?
Lauren,
Lauren. What's VREL?
still working it out.
They're still working it out. Okay, fair enough. Anybody know what VREL is? Yes, sir. You right there. Your name, please? Dan. What's VREL? 0. Dan says VREL is 0. Pretty radical. What's the basis? Yeah, you get a thank you from Isabella. Bailing her out there. Why?
E is fixed to the rigid body.
That is it. Rings the magic bell. The VREL is 0 because the point in question, unlike the figure I've drawn up here, this example I've drawn here, the point of interest is fixed to the body. So VREL is 0. Doesn't that make life easy for Isabel? VA goes to 0, VREL goes to 0. What are we left with?
Omega cross r.
Exactly, omega cross RAB. And by the way, how long is RAB? 2R. 2R. They're perpendicular. Omega and R are perpendicular, so you get the full value. Hey, okay. Isabella was right. So, Lauren, Isabella said A is the instant center. All right, now it's Lauren's turn. Lauren comes along, says, I don't see it that way. I want to do it this way. Because, after all, I get to choose. So I am going to call this okay. Lauren, what have you done? Now we got here's your choice. And again, in both cases, the little x and little y, or the, shall we say, the unit vectors are here and here. So that's not really part of the problem here. So what we're trying to do is apply that formula again. V sub A is 0 as before? No. What is it?
Omega r.
Yeah, exactly. Now V sub A is not 0. It is in fact omega sub r, omega r times I. And so, how about VREL though? You got a VREL problem? Still 0, for the same reasons before. Perfect. So what is the velocity of this point? Just omega r, because r sub AB is simply from here to here. All right, and once again, v sub b now comes out like that. Everybody got it? Everybody says long-winded answer to the question, can A be the, or is A the instant center? Answer is sometimes, sometimes not, because A and the body coordinate system are a matter of choice, whereas the instant center is a matter of the kinematics, a matter of the physics of the matter, so to speak.